want to quantify that difference and show just how polar a molecule is with something called dipole moment. So, dipole moment is represented by the variable mu. So the equation for dipole moment is mu equals Qr. So mu being dipole moment, Q equals our charges. We want our charges, normally we'd speak of charges in terms of E, like if we say something has a 1 plus charge, a 1 negative charge, a 2 plus charge, we're talking in terms of this little E, like electrons. However, for this equation, we would prefer to represent charges in terms of coulombs with a C. R stands for the distance between nuclei, the bond length. So if we were to use this equation, then the greater the charge, or the greater the bond length, then the bigger this should be. So if Q goes up or R goes up, mu should also go up. So the units, I should go back, the units for mu are debis. You'll have to find out, or I should have found out, how exactly you pronounce these things, which is represented by a big D. So one of these equals 3.34 times 10 to the negative 30th coulomb meters. Now, normally when you find the bond length between nuclei, that might be expressed as angstroms. So one thing of note is that if debis or whatever have meters in them, this is angstroms. At some point in your math, you're going to have to convert angstroms to meters. And you also have to convert your charges, E, into coulombs. And so that relationship is simply this. 1E equals 1.60 times 10 to the negative 19th. These are relationships that you should write down for sure somewhere and possibly even memorize. Oh, yes, 1 angstrom also equals 10 to the negative 10th meters. Okay, so let's see how this is applied. Let's say you are given the example, if you know that hydrogen chloride or hydrochloric acid, if dissolved in water, has a bond length of 1.27 angstroms. And you are going to assume that the charges are 1 plus and 1 negative. So the magnitude of the charge would be 1e. What is the dipole moment? Well, going back to our equation, mu equals Qr. First, we start plugging in our numbers. So mu equals Q, which we said was 1e, times R is 1.27 angstroms. Well, since we want, let's remember that we want D's all the way over here. and D's equal coulomb meters. So first thing, we have to get rid of these charges and turn them into coulombs. So the way we do that is if I have 1E here, and 1E is 1.60 times 10 to the negative 19th coulombs. So that gets rid of my E's. But now I have to convert angstroms into meters. So I put 1 angstrom here, and then I have 10 to the negative 10th meters up here. Finally, since we want our final answer to be in debis or debis, 1 debi is 3.34 times 10 to the negative 30th. Notice the coulombs and meters. So now, coulombs and coulombs cancel out. Meters and meters cancel out. And if I do this math, my answer should be about 6.08 D. Now, what if I were to go the opposite way? To give you an example. So here again is our equation, mu equals QR. So if instead you had, you knew that experimentally for HCl that the dipole moment was 1.08 D. And if you remember from the question that I just asked you, that if we have 1.27 angstroms for the bond length, then how about we solve now for the actual charge? So if we are looking for Q now, we can convert this equation to mu divided by R will give us Q. So going back, 1.08 D over, we see 1.27 angstroms. Well, if we are looking for Q, we eventually want our answer to be in E's. So I first want to get rid of D's. So again, going back, 1D is 3.34 times 10 to the negative 30th coulomb meters. That was a conversion factor that I showed you earlier. So D's and D's cancel out. Angstroms and meters, they both represent length, but they're not compatible. So I'm going to have to convert angstroms to meters. So since angstroms are down here, I want to put the angstrom label up here. If I have 1 angstrom, I have 10 to the negative 10th meters. So now meters can cancel out. I want my answer to still be in E here. So if I have 1E, I have 1.60 times 10 to the negative 19th of C. So now my C's cancel out. My angstroms canceled out. And so I am left with the label E. And if I do the math, multiply everything on top, divide by everything on bottom, my answer should be 0.178 E. So what this means is if I redraw my molecule of hydrogen chloride or hydrochloric acid, this means that for chlorine, we have a partial negative charge of 0.178. or I could write it this way, 0.178 negative E, or 0.178 positive for hydrogen. So notice how this is less than 1 because there was not complete electron transfer. So this does agree with the fact that we've already determined that this is a polar molecule, that we should have partial positives and partial negative charges.